I would like to talk a little bit about the status, different applications, use cases. I thought I want to talk a little bit also of the challenges. So the challenges we are currently facing, and especially how it will proceed when we look into the future. Because I mean, we're basically just at the start of what 5G is, of 5G, how to realize this, how to make the system a reality, all the requirements, meeting them by applying the technologies in the right way. Yeah, so first here some key architecture components of the 5G system. What I see as a key component of the 5G system, which come into play compared to what we had so far in the previous generations, is something here, for example, the so-called service-based architecture. Yeah, basically it's not static anymore. We can introduce new services into the system. Basically, we can adapt the whole life cycle of services, introducing, removing services. We have something which is called access disaggregation, which is a big topic now. Yeah, you don't have monolithic systems anymore. Yeah, you break the system down into smaller pieces, again related to the service-based architecture concept, and this goes down even into the radio access part. Yeah, where you have then antennas, the baseband processing, centralized units, distributed units for the signal processing, and so on. So this is an important aspect. What I also want to mention here is the concept of virtualization, which plays a bigger and bigger role. Yes, so in previous generations you had integrated systems comprising hardware and software from different vendors. This is also open now, so you will have new interfaces. You separate basically the hardware from the software, which means that you have opportunities to make, for example, use of cloud solutions in order to run your network services or functions actually even in outsourced environments. Yeah, so you can really focus on specific aspects and provide your expert services. So the concepts, some have mentioned already, especially when I refer to the last presentation, the edge computing, because we have these requirements in 5G that we want to have ultra low latencies. And as said before in the previous presentation, especially for the car industry, it's very important. So what we do in general in 5G will bring the computation power, the services more to the customer, so closer to the antenna, if you want. Another important aspect is the so-called network slicing. You have a huge diversity of services, huge diversity of requirements. This will be all possible to provide, to fulfill these service requirements to meet the demands on a single physical network. You do this by establishing so-called network slices, which can be seen as some kind of virtual networks with different KPIs, different treatment priorities, and so on the same hardware. So this goes hand in hand and also with the edge computing. One topic which is currently a big issue in Germany with campus network issue. So you have localized networks, specialized, for example, for industry applications, where you have restricted access. Yeah, it's not a public network, it's a non-public access network offering specific services, making use of edge computing, for example. So you combine these technologies. So this is a tool set we have. If you take this all into account, you have seen already, I mean, we have very high degree of flexibility in this 5G system. Yeah, one system which has so many parameters. We have a high degree of heterogeneous deployments. Yeah, also this was already mentioned before. So we have, for example, different frequency ranges which are supported. Yeah, 5G is more or less frequency agnostic in a certain frequency range, but you have to know which frequencies, for example, to use in which scenarios, for which use cases. So this brings us into a situation where we face a lot of challenges. So we have now a huge tool set, increasing even more and more features for the future. And I think one important aspect here that 5G is not just a new air interface like we had in previous generations. We have a lot of new technology at the air interface. The 5G is more like a complete new ecosystem. And the air called 5G new radio is just one part of this. So we have much more, which makes the system very complicated, very challenging, but offers also huge opportunities, as we have seen. What I want to talk a little bit about is so-called smart and flexible networks for the digital transformation. And this basically captures what we want to do. As I said, we have a huge degree of flexibility. We have virtualization, we have separation from hardware and software. We support different slicing concepts. So at the end, what we have, we have from different customers, either it's businesses, industry, or just public use cases. We have sets of requirements. Based on these requirements, we at the end have to establish our network configuration adaptation in order to meet these requirements and to go into the production, whether this is now services or products. We have different cases. And the aspects which come into play here are the network function virtualization. As I said, we have a separation of hardware and software. We have different vendors. So you will have now vendors specified on hardware. You will have complete new players out of the US who focus on software development for network operation. Then we have a feature called software-defined networking, which overlaps with the network function virtualization. And as I'm pretty sure you're all aware, we have more and more what I call here cloudification. So we bring services into clouds. We have cloud operators. And here we come to a point that you can even outsource your network operation into cloud centers, because these are processes at the end. This is software. And if you want to operate such a system, so you need different steps. You need a configuration of the network. When the network is established, it's configured, you have to adapt the configuration parameters on many different layers, from the physical layer of the interface up to some parts in the core network. You have some constant possibilities to adapt parameters or even complete features of the network. If you go to a higher level, you have to take into account the orchestration of the different functions. It becomes quite complicated systems. You have many degrees of freedom, as I mentioned before, and you want to try to optimize it. So what you do on the operation part regarding configuration, adaptation, and orchestration, you go more and more into this direction that you do comprehensive data analytics. So monitor different functions of the networks. You monitor different interfaces and try to define rules for the configuration and adaptation. And one important technology is the machine learning concept coming out of the artificial intelligence family. So we basically start combining data analytics with machine learning in order to have adaptation of the parameters, orchestration, in order to fulfill the requirements, to meet the needs. And in the network itself, a lot of what's currently happening is in the direction of opening the architecture by introducing new interfaces. I call this here open interfaces. When you have new interfaces, you can offer new services, new players come into the game. A lot is happening in the direction of open source projects for optimizing networks or providing different functions. So this is basically the field where a lot is happening currently now from research and development point of view. And when I go to the challenges, I see one of the main challenges at the moment is that we have to understand the requirements. As you have seen already before, there are many different requirements regarding throughput, latency, jitter, stability. We have to understand the conditions. For example, changing the carrier frequency, 700 megahertz, 2.1 was mentioned before, up to 3.6, 3.7, or 26 gigahertz, which becomes now an interesting topic. These have completely different propagation properties, for example, depending on the environment. So you have to understand these conditions, you have to understand the technology, and you need mutual understanding. So on this level, we need basically a lot of harmonization, also transnational. So this is where the European Union, for example, they established this new research framework, Horizon Europe. Maybe you heard of this. They're covering 21 up to 27. So the next years, there was a huge funding of 100 billion euros in order to harmonize the efforts here. As I said, when you understand the requirements, condition, technology, you go into the optimization of configuration, adaptation, orchestration, which is important. And for the specific industries, you have to provide target-oriented solutions for the provision of quality of service. Further aspect is that when you set up a network, either if it's a campus network, which is locally restricted, or it's more like a cellular network or part of a cellular network, you have to perform a quality of service predictions. Because you will not just set it up and then test it. I mean, you have to do some evaluations in advance. You want to provide, for example, for the car industry, it's important, car-to-car communications. When you have streets, you need predictions where it's critical, where it's working fine. So this is a huge part of the work we do here in our lab. So we do a lot of measurements. So this is an example I put here. So we have BMW in Leipzig, northern area of Leipzig. We have new 5G sites there. And then it's exactly what I mentioned. So we have to do quality of service prediction to see what is possible, where are critical issues in order to go into the feedback loop and optimize the configuration of the system. This is a lot what's currently happening here, because if you set up a campus network, you have to take all these conditions into account in order to optimize it. Second part, beamforming is here an example was also mentioned before. This makes it very challenging. I mean, you can do these nice beams, as mentioned by the colleague from Lufthansa before, they can be very narrow, but you have to make sure that you hit the right spots. So there, for example, we do also a lot of simulations in order to predict, for example, how many beams you need, what kind of antennas do you need. So this is basically the part where you have the biggest challenges currently. And to conclude this short overview, I thought, okay, I can try to give a very, very short outlook into what's coming next. So what's next? Outlook 2030. I put it 2030 because, I mean, as mentioned in the first presentation, roughly every 10 years you will have a new generation. So the research starts already in the direction of 6G. 30, or as I said, Horizon Europe, the program which goes into the preparation of 6G. So what we will see in the future is terahertz communications, so basically even higher frequencies. We have more bandwidth, higher capacity, shorter range. And so the system becomes even more diverse in the future. We will see more distributed MIMO. MIMO means multiple input, multiple outputs. So you increase the number of antennas. They are distributed over areas. They operate together. Again, this puts a lot of pressure into the optimization and adaptation thing, but can achieve huge capacity gains and also reliability gains. The more antennas you use for serving the user, the more robust becomes the system. We will see in the future more and more tight integration of artificial intelligence for automation, also configuration, adaptation, because we have this incredible feature set, but you have to understand it. And currently we're in the learning phase. We have the new tools, and we have to learn how to use them in order to use them in the right way. So I always imagine this as some kind of fully equipped gym we have currently. We have all these fancy devices where we can exercise, but we have to understand what we actually want to achieve. We need some kind of personal training at the end in order to know which devices we have to use, which features we have to combine in order to achieve our goals in the most efficient way. And there, AI concepts, like machine learning or deep learning, can be very, very helpful. So this is what we're currently studying. And we will see a further increase in the flexibility of topologies and deployments, because the networks become flexible in a way that you will have the network services more demand-driven. So you will see the network services there where you really need them. And the spatial dimensions and the time dimensions as well, because the network doesn't have to be there all the time. At certain times it's required, certain times not. and combine it with the energy efficient aspect. And the last point I want to put here, it's here called zero energy devices. Yeah, in the future, you will have devices like sensors. They don't need their own power supply because they can get the power supply over the air interface. And so you trigger them and you get a response in order to improve the energy efficiency of the whole system. So there's a lot to do. And we're basically just at the start, understanding the set of features we have now, the tools, and we have to learn how to use them in the most efficient way to meet the individual demands.